Howdy, howdy. This is Mr. Potter. In today's lesson, we're going to extend what we were talking about in our previous lesson. In our previous lesson, we were talking about how to solve differential equations, where dy dx equals some relation of x and y. And we talked about a couple of ways that we could do this. One way that we could do this is we could actually find an antiderivative. The idea that if I want to take the derivative of a function, what I would do is I would decrease the exponent by 1 after multiplying the coefficient times that old exponent. And the idea that I could work backwards on this power rule by adding 1 to the exponent and dividing by my new exponent to end up getting a original function, which of course this isn't really one function, but it's a family of functions. So we talked about the idea of an antiderivative, but one other thing that we talked about is the idea of a slope field. The idea that if I draw x and y axes and I talk about the slopes at a particular point, that I can use these slopes to come out with a graphical solution to a differential equation. So we have these two ways that we've already talked about to coming up with either a solution or an approximation to a solution for a differential equation. What I want to talk about today is I want to talk about a numerical method for coming up with a solution to a differential equation, and it's called Euler's Method. But it's actually based on a concept we talked about back in chapter 4, this idea of coming up with a linear approximation. One of the things that we notice is that if I'm looking at a differentiable function, I know that a tangent line is a very, very good approximation as long as I'm near the point of tangency. So I'm going to start off with this very difficult differential equation. dy dx equals 2x. And you know, there's a whole infinite number of solutions to this differential equation. But there's only one solution that passes through the point 1, 1. And if I want to approximate y at 1.2 using a tangent line, I have to come up with a tangent line that's going to pass through this particular x value and this particular y value, whose slope is going to be determined by the derivative at that particular x value. So for our purposes, x equals 1, y equals 1, and my slope is going to be 2 times my x coordinate. So my slope is going to be 2. And I can come up with a tangent line, y minus my y coordinate equals my slope times x minus my x coordinate. So y equals 1 plus 2 times x minus 1. So I can find what y of 1.2 is approximately by taking 1.2 and substituting it into this linear function. So I get y equals 1 plus 2 times 1.2 minus 1, or y equals 1.4. Now, I'm being a little bit disingenuous when I talk about this being a difficult differential equation. The antiderivative of 2x is going to be a family of functions x squared plus c. And if I want my y equals x squared plus c to pass through the point 1, 1, I certainly can substitute and solve for c. And so I know that the particular solution that I'm dealing with is just y equals x squared. And I also know that 1.2 squared equals 1.44. So this is a fairly good approximation. It's not anywhere near being exact, but this technique that we're going to be talking about, this Euler's technique, is going to be a better approximation. The idea is that if one tangent line is good, then 2 should be twice as nice. So I'm dealing with the exact same situation where dy dx equals 2x, and I'm starting at the point 1, 1, and I want to estimate y of 1.2, but the idea is that I could do 2 tangent lines. One tangent line that's kind of halfway, and then a second tangent line that kind of continues on. The idea is if I do these 2 tangent lines and kind of bend my slopes, so I'm following the contour of this parabola, I should get a better estimate for the solution of this differential equation. And again, I know this is easy. I'm going to do two examples later on that are much more difficult. But right now I'm just illustrating the point here. So I'm starting off with my original x coordinate. X was equal to 1, y is equal to 1, and my slope is 2 times my x coordinate. My slope is 2. And this tangent line is the exact same tangent line we just talked about. But in this case, instead of substituting in 1.2, I'm going to use this as my guide. My delta x is 0.1. So I'm actually going to be substituting 1.1 into this. And so what I find out is, in this case, y equals 1.2. So what I'm saying here is that my tangent line passes through the point 1.1, 1.2. So for this second tangent line, I'm going to be using this point as my jumping off point. X is 1.1, y is 1.2, and my slope is 2 times my x coordinate, or 2.2. And so now when I do my tangent line, I'm using my new x coordinate, and I'm using my new y coordinate. And I'm using the correct answer. X minus 1.1. So if I now substitute 1.2 not in my original tangent line, but in this new tangent line, this modified tangent line, this one that's a little bit closer to my parabola, then I find out that y ends up being 1.2 plus 2.2 times 0.1, or y is 1.42. Now, I want to do some comparisons here. If I just use one tangent line, then I ended up with a y of 1.2 was approximately 1.4. That's what we just did on the previous screen. But if I use these two tangent lines, or what we call Euler's method, then my y of 1.2 is approximately 1.42. And keep in mind that the actual solution, y of 1.2, because it is a parabola that passes through 1, 1, is going to be 1.2 squared, or 1.44. And notice that by taking this second tangent line, a tangent line that kind of reaches halfway, and then a second one that does a jumping off point, I end up with a much better approximation. I end up with a much better estimate of what my function should be when x equals 1.2. So I want to talk about why this works. So I'm going to draw a parabola here. Horrible parabola. Horrible x-axis. But the idea is I want to know what's happening at this point here, at the point 1, 1. So if I draw just the tangent line here, there's my tangent line. And of course, my drawing is not to scale, but if I look at what's happening at 1.2, my tangent line is actually quite a bit away from this point on the parabola. But if I wait and go halfway up to 1.1, and at this point on the tangent line, come up with a new tangent line, a tangent line that's parallel to my graph. Notice that the approximation using the second tangent line is much closer to the actual function's value. I'm kind of using tangent lines that follow the contour of my curve. And this is why Euler's method works. The more delta x's that I use, in other words, the more refinements that I make to make my tangent lines contour more and more to the curve, the closer my estimate's going to be. So we run into the classic mathematical issue of time versus accuracy. The question is, how much time do I want to invest to get an accurate solution? We already have this idea of tangent lines, which is a fairly accurate solution. And so on the AP exam, they usually ask it where I'm only going to end up taking 2 steps. Remember that the AP is a timed test, and they want to see if you understand the concept. 2 steps is enough to show that you understand the concept. Now, as I've mentioned before on the past few pages, I'm dealing with a very simple derivative, and it has a very easy solution to determine. But I can use this with any formula for y prime. So I've got this example here. I've got y prime equals 2x minus y. And I'm starting at the coordinate 0, 0, and I want to approximate approximate 0.4 comma with delta x being 0.2. So I'm going to go through this process of finding a tangent line. Again, starting at 0, 0. So this is my x, this is my y. X is 0, y is 0, and my slope is going to be my derivative at the point 0, 0. So it's going to be 2 times x minus y. Well, amazingly enough, my slope is 0. And so my tangent line is y minus 0 equals 0 times x minus 0, or basically y equals 0. I have a horizontal tangent line at this particular point. And if I'm letting delta x be 0.2, I'm using this line to approximate 0.2, but if it's a horizontal tangent line, it's 0. So what I've got here now is for my second iteration for Euler's method, x is 0.2. Y is what we just determined, 0. And my slope is going to be my derivative at my x coordinate 0.2 and my y coordinate 0. So this is going to be 2 times my x coordinate minus my y coordinate, or 0.4. So now I have a non-horizontal tangent. Obviously, just using this tangent line, since it was a horizontal tangent, is just going to give me a constant 0. But now using Euler's method, getting a second tangent line that's a little bit farther away, a little bit closer to my curve, I'm getting something that follows the contours. So I'm doing my tangent line. Y minus my y coordinate equals my slope times x minus my x coordinate, or y equals 0.4 times x minus 0.2. So I want to take this 0.4. I want to approximate 0.4, and I'm going to approximate by substituting it into this function. So this should be approximately equal to 0.4 times x minus 0.2, or 0.4 times 0.2, which would be 0.08. So y of 0.4 is approximately equal to 0.08. Now, at this time, we don't have a way to find a solution to this differential equation. As a matter of fact, the best that I can do at this point is not find the antiderivative of this, but instead to graph a slope field and find a solution that's passing through the origin. That's really the best guess that I can do. But notice that Euler's method gives us a much more precise approximation. There's no way that I could get 0.08 by looking at a slope field. So all that we're doing is we're finding tangent line approximations, but we're doing it in two steps. One step using the original data that they gave us. And one step that uses this delta x to determine a new x, a new y, and a new slope. So I want to do one more example of this. I want to take a look at this differential equation. Y prime equals xy, starting at 1, 1. And I want to approximate 1.2 with delta x being equal to 0.1. So I'm starting off with the x value and the y value that they gave me. And my slope is going to be equal to x times y, which in this case is 1. So I've got y minus 1 equals my slope times x minus 1, or y equals 1x. This is my approximation. I want to get from 1 to 1.2, but I want to take baby steps. I want to go 0.1 steps ahead. So I want to substitute 1.1. Y of 1.1 is approximately equal to 1 times 1.1. And now I'm ready to do the second iteration. The thing is, if x is 1.1, y from our approximation here is 1.1, and my slope is going to be x times y, which is 1.21. So my tangent line is y minus 1.1 equals 1.21 times x minus 1.1. And now I'm ready to approximate what's happening at 1.2. Y equals 1.1 plus 1.21 times 1.2 minus 1. I'm ready to substitute this into x. So I've got y equals 1.1 plus 1.21 times 0.1, or 1.1 plus 0.121 or 1.221. This is my approximation of y of 1.2 at this particular value. And again, notice that this Euler's method, even though it's giving us an approximation to the solution of a differential equation, this certainly is much more precise an approximation than I could ever achieve with a slope field. Remember, a slope field is going to give me a graphical approximation. It's going to give me a general trend of my solution. We will have the ability to solve a differential equation like this in this course. And we'll be talking about that later on in this chapter. Main idea for Euler's method is when I'm dealing with Euler's method. Euler's method is really two or more linear approximations. And the whole idea is that we want to contour our tangent lines to approximate the graph. And what we're going to be doing is we're going to be using the previous x and y to determine a new x and y. And we're going to be using the same slope formula that we've been dealing with and these x and y coordinates to come up with a new slope. This gives us our second tangent line. I could do this 3 times and get a third tangent line. I could do this 4 times and get a fourth tangent line. But all I'm doing are tangent lines. That's the whole idea behind Euler's method. It's a wonderful way to approximate a solution because tangent lines are so close to a curve at the point of tangency. So once again, this is Mr. Potter. Thank you for watching. Have a great day.